IOE 413, Mathematical Preliminaries Study Guide. This problem begins with a fairly extensive optimization problem. Let's write it down here. It's a maximization problem. So we're maximizing z is equal to 5x1 plus x2 plus 3x3 plus 4x4 minus x5. That's the objective function. Then there are three constraints. The first one is x1 minus 2x2 plus 4x3 plus 3x4 minus 2x5 is equal to 20. That's an equality. This will come back as an important part of the problem later. Second constraint is negative 4x1 minus 6x2 plus 5x3 minus 4x4 plus x5 is less than or equal to 40 on the right hand side. Third constraint is 2x1 minus 3x2 plus 3x3 plus 8x4 minus 15 x5 is greater than or equal to 50 on the right hand side. And then we have x of I is greater than or equal to 0 for I is equal to 1, 3, and 5. And x of I is less than or equal to 0 for I is equal to 2 and 4. That's the problem that we'll be working with. So let us begin our 6-step process for creating duals with step 1. I'll write that up at the corner up here to remind me that we're doing step 1. Step 1 involves creating what I call the pseudo matrix form of the problem. It's very much like writing it down in terms of matrix algebra, but with a little bit of difference. What we do is we write down our constraints with as matrices with a bunch of constants in it, and then we separately write out the equality and inequality for each one of the constraints. We need to do that to keep our bookkeeping straight. You'll see why that's important as we go along. So let's begin our problem by writing max z is equal to, and now we do the objective function as a row vector 5, 1, 3, 4, -1, 5, 1, 3, 4, -1 times x. So we're not going to write out all the different components of x. We'll just treat x as a column vector. And then we're going to write down the constraints here. I'm going to write down 1, -4, and 2 to get the dimensions here of this bracket that we need to make it all look right. Second column is -2, -6, -3. Then we have 4, 5, 3, 3, -4, and 8, then -2, 1, and -15. Now notice what I've tried to do here as carefully as I could. Line up the columns of the constraint matrix right underneath the numbers in the objective function coefficient vector. If you line them all up, it will make creating the dual much easier. Then we have a column vector x, and this is where we write down the first constraint is an equality, the second one is a less than or equal to, and the third is a greater than or equal to. On the right hand side, we do 20, 40, and 50. And then we put the sign restrictions on our variables. And that will be x1 is greater than or equal to 0. x2 is less than or equal to 0. x3 is greater than or equal to 0. x4 is less than or equal to 0. And x sub 5 is greater than or equal to 0. That's our linear program in what I call pseudo-matrix form. Step 2 of the process involves associating dual variables which each constraint. So I'm going to write down here step 2, and we'll associate pi 1 with the first constraint, pi 2 with the second constraint, and pi sub 3 with the third constraint. So each constraint has a dual variable associated with it. The equality has pi 1, the less than or equal to has pi 2, greater than or equal to has pi 3, and that's step 2. Step 3, I'll write that up here just to remind ourselves. Step 3 involves creating the dual objective function. Since our primal was a maximization problem, our dual will be a minimization problem. So we have minimize. Instead of z, we'll say v. And we'll write out the dual objective function as the product of a row vector of pi's and a column vector. And the column vector is the right-hand side of the primal. 20, 40, and 50. So that is just be minimize b is equal to 20 pi 1 plus 40 pi 2 plus 50 pi 3. So now we're going to do step 4. And step 4 is creating the dual constraints. Let's make the first dual constraint. The first dual constraint corresponds to the first primal variable. So for every primal variable, there's a dual constraint. Okay? And so the coefficients on the first primal decision variable, that on x sub 1, is this column here. Right? And the corresponding coefficient to the objective function is 5. And this is why I went to so much effort at the beginning to write out the pseudomatrix form so that all of the coefficients lined up in columns very neatly. So what we do is we create a row vector with our dual variables, pi sub 1, pi sub 2, and pi sub 3. And then just drop in our column here from the constraint matrix, 1 minus 4, 2. So we have, when we multiply this out, we have pi 1 minus 4 pi 2 plus 2 pi 3. And the right-hand side of our constraint is going to be the coefficient from the objective function, 5. So that's 5. Now what we need to do is figure out what we put in here. Is it a greater than or equal to, less than or equal to, or equal sign? To do that, we'll go to what I will refer to as our primal dual table. Continuing step 4, we determine the direction of the inequality of the dual constraint by using this grid. And we're working with in the primal as a maximization problem. And our decision variable for x sub 1 that corresponds to the column that we're working with to make the dual constraint, x sub 1 was a greater than or equal to. It was x sub 1 is greater than or equal to 0. So you follow this line over to the right, and you get the dual constraint is a greater than or equal to form. So that's what we'll use. So now we know that what we need to put in here is a greater than or equal to sign. When you write this whole thing out, you get pi sub 1 minus 4 pi sub 2 plus 2 pi sub 3 is greater than or equal to 5. And that is our first dual constraint. Now let's do our second dual constraint. And that will be driven off what's going on with our second primal decision variable. So that's the second column of our constraint matrix and the second element of our cost coefficient vector. So again, let's write down pi sub 1, pi sub 2, pi sub 3 as a row vector, and then drop in here minus 2, minus 6, minus 3, and the right-hand side is going to be the coefficient in the cost vector, so that's just 1 on the right-hand side. So now what we need to do is figure out whether this is going to be a greater than or equal to, less than or equal to, or equals to sign right in here. And we do that by going back to our primal dual grid. So you will recall that in the statement of our primal problem, x sub 2 was less than or equal to 0. So our primal problem was a maximization. Our decision variable is less than or equal to 0. So the corresponding constraint in the dual, to get there we go over to the right with this arrow. The corresponding form for the dual is less than or equal to in the dual constraint. So for this constraint, we drop in less than or equal to, which gives the constraint minus 2 pi 1 minus 6 pi 2 minus 3 pi 3 is less than or equal to 1. And that's our second dual constraint. We now have 3 more dual constraints to construct, and I'm not going to go through the step-by-step details for each one. Instead, what I'm going to do is ask you to do that, but notice the patterns that exist here. X sub 1 is greater than or equal to 0, so is x sub 3, and so is x sub 5. So the dual constraints corresponding to these 3 decision variables will be of the same form. The exact coefficients will be different, but the structure in terms of the equal to, greater than or equal to, or less than or equal to will be exactly the same for these 3 variables. Now, we also did x sub 2. That was our second dual constraint. The second dual constraint corresponded to the x sub 2 primal decision variable. And x sub 4 is also less than or equal to 0. So these 2 decision variable sign restrictions are the same, and that will drive the same form in the dual for the fourth and the second dual constraints. Now that you've learned how to create dual constraints, let's write all of them down. So the first one is pi 1 minus 4 pi 2 plus 2 pi 3 is greater than or equal to 5. The next one is minus 2 pi 1 minus 6 pi 2 minus 3 pi 3 is less than or equal to 1. And then we have 4 pi 1 plus 5 pi 2 plus 3 pi 3 is greater than or equal to 3. Then we have 3 pi 1 minus 4 pi 2 plus 8 pi 3. Let me just clean up that 8 a little bit. And that's less than or equal to 4. Then we have negative 2 pi 1 plus pi 2 minus 15 pi 3 is greater than or equal to negative 1. And those are all the constraints for the dual of this problem. Now that we've made our dual constraints, let's figure out what the sign restrictions are on the dual variables. And this is step 5 of the 6-step process that I went over in lecture notes. So the sign restriction on the first dual variable pi 1 is driven by whether this is a maximization or minimization problem and what this is right here. And this is why I went to such effort to line up the different equality and inequalities for each constraint and line them up carefully so they would match up with each dual variable, because we need to look at the dual variable, the maximum min of the primal problem, and exactly whether the constraint is less than or equal to, greater than or equal to, or equals to. So in this case, it's equals to. It's a maximization problem. So let's go look at our primal dual table and figure out what the sign restriction on pi sub 1 should be. So we use this grid to determine the sign restriction on the dual variable. Remember that our primal is a maximization problem, and we need to now look at the constraint that's associated with the dual variable, and that constraint, when we come down in this column, is equal. We head over to the right, and we get unconstrained. So what that means is that pi sub 1 is unrestricted. It's just on the real line r. Okay, so pi 1, sometimes we write is UNR for unrestricted. Same thing here in the table, it says it's unconstrained. So now let's look at the second primal constraint and the sign restriction on the second dual variable that corresponds to it. So to get the sign restriction on pi sub 2, we look to see this is a maximization problem, and the relevant inequality here is less than or equal to. So it's the less than or equal to and the max that will drive the sign restriction on pi sub 2. So now let's figure out the sign restriction on the dual variable. This is a maximization problem. The constraint is a less than or equal to. So we go over to the right, and we get a greater than or equal to restriction on the dual variable. So the second dual variable, pi sub 2, is greater than or equal to 0. Now let's figure out the sign restriction on pi sub 3. And that's driven by the fact that it's a maximization problem, and the direction of the inequality in the third constraint, which is greater than or equal to. So we look at greater than or equal to and max, go to a primal dual grid or table, and we'll figure out the sign restriction on pi sub 3. So the sign restriction for pi sub 3 is driven again by the fact that the primal is a maximization problem. And we go down and we'll look at the constraint. So we see it's a greater than or equal to form. Go over to the right, and you get less than or equal to 0. So this means that pi sub 3 is less than or equal to 0. Now we've shown you with those three different kinds of examples of constraints: equality, less than or equal to, or greater than or equal to in the primal for a maximization problem. We've shown you how those translate into restrictions on the dual variables. Now we have everything that we need to write the full dual. And let's do that right now. So our dual will be minimize v is equal to 20 pi 1 plus 40 pi 2 plus 50 pi 3. And then for sign restrictions, pi sub 1 is, we'll write it UNR for unrestricted. Pi sub 2 will be, all right, pi sub 2 is greater than or equal to 0. And pi sub 3 is less than or equal to 0. And that's our full dual problem. Now we're ready for step 6, the final step in my 6-step process for making duals. And step 6 is checking. And there are 3 kinds of checks that you can do, 2 that are simple, that are easy to do, and 1 that takes more work. We'll talk about all 3. The first one is making sure that you have the right minimization and maximization. If your primal is a max, your dual is a min. If your primal is a min, your dual is a max. Max goes to min, min goes to max. Our primal was a max, so our dual is a min. Check, that's okay. The second check that's very easy to do is to inspect your dual formulation to make sure that there are no primal variables. In this case, our primal variables were x's, so what we want is there are no x's. There are no primal variables, and that's indeed true. Check. So those two checks are easy to do, and we've done them. The third is a lot more effort, and that's creating the dual of the dual. The dual of the dual is the primal. If you have the time on an exam to go through and do that, that's a good thing to do to check your results. If you don't have the time, you certainly should check to make sure that max goes to min, min goes to max, okay? And that you do not have any primal variables in your dual formulation.